Welcome to Temperature Composition Diagrams. Alright, so in order to discuss distillation, we need to have a temperature composition diagram, which is a phase diagram in which the boundaries show the composition of the phases in equilibrium at various temperatures. So this is at a given pressure, which generally is 1 atmosphere. Right, so know that the liquid phase is in the lower part of our diagram, while the vapor phase is in the upper part of our diagram. So here we have temperature on the y-axis and composition, so the mole fraction of our first component A on the x-axis, the horizontal axis, because we're calling this ZA. So remember that Z is the mole fraction of our entire system. And so we're going to say that XA or chi A is the mole fraction of A in our liquid phase, and then YA is our mole fraction of A in our vapor phase. So, again, the lower part, so below the blue line is liquid, above the reddish line is the gas, the vapor phase, and in this case we can't get in between the two lines. Right, so suppose we heat a composition, or we heat a liquid of composition A1, so we're down here, we have some mole fraction. So as we heat, we're not changing the mole fraction, we're not changing the composition, we're just moving up this dotted line. So once we get the temperature up to T2, then now we've reached the intersection between this dotted line of the mole fraction of A1 and this blue vapor pressure curve here. And so, boiling curve. And so, now our liquid is boiling here at this temperature, and the liquid composition is given by A2, which again is the same composition as A1. The vapor, however, doesn't have that composition. The vapor has the composition that's over here at A2 prime. So it's the same temperature, but the blue line is the composition of the liquid, the red line is the composition of the vapor. And so this means, and then we join them together with this solid black tie line. So know that our vapor now, A2 prime, is more volatile, is richer in the more volatile component. We've enriched it in the more volatile component. We're defining the more volatile component as A. We're calling this our solvent. Most of the time, we call A the solvent. A is defined as our more volatile component. That's how we're talking about it here. If A somehow becomes less volatile, well, then we're going to switch our labels of A and B. So A will always be our more volatile component. So our vapor is more enriched in A. We're moving to the right on the composition axis. And that means that our vapor is preferentially enriched in the more volatile component compared to the liquid phase. So now that means that given the location of A2, point A2, we can then say what the vapor composition is, A2 prime, using the location of this tie line. Again, this is a horizontal line. It's at the same temperature. So A2 and A2 prime are at the same temperature because the vapor and liquid exist at the same temperature. And then we can also say, well, now we know what the boiling point of our original liquid mixture would be. Right, so in a simple distillation, our vapor is withdrawn and then it's condensed. So we just do this one time. We heat up our liquid phase until it boils, or until a portion of it boils, and we take the vapor phase, we cool it back down to condense it back into a liquid, and then we're done. And so simple distillation can be used to separate a volatile liquid from a non-volatile solute. So say if we want to separate volatile water from a non-volatile like sodium chloride, we can just heat up the water. The water will evaporate at around 100 degrees C, slightly higher. depending on the concentration of the sodium chloride. But the sodium chloride won't evaporate. The vapor pressure of sodium chloride at 100 degrees C is essentially zero. So that's simple distillation. However, if we're looking at fractional distillation, then the boiling and condensation is repeated successively. So we do this again and again and again to get a more pure or a larger change in our composition. So if we have a case like this, where both of our components have some significant vapor pressure, we've only enriched our vapor some amount. I mean, in this case, we've taken it from somewhere around 0.2 to somewhere around 0.5 mole fraction of A. But if we want to get pure A, well, we need to keep going along this axis. We need to move to the right more. And so that's when we would need fractional distillation. So we'll distill, and then we'll condense our vapor phase back into a liquid, and then we will then move that to a different container and heat it back up again, and continue doing that with successive vapor phases until we get a pure enough liquid with them. Alright, so fractional distillation is used to separate volatile liquids. So after the first vaporization cycle, then the liquid now has a composition given by point to A3. So we started out at A1, we heated it up, we vaporized it, and that means that the vapor has this composition. Well, if we condense that back down, then we're at some temperature, at least this low, our liquid has the same composition as the vapor did, provided that we condense it in a different place than this liquid is at. And that means that now that liquid has a boiling point of T3. And then if we heat that liquid again, now it will vaporize, and we'll get a vapor of A3 prime over here at this point. And so now we've heated up our initial mixture, we vaporized it, we condensed that vapor, and we vaporized that liquid again in a different place to keep the two vapors separate. And now we can condense that again, and you notice that our boiling point is decreasing with every purification cycle that we go through. And so now we have a liquid with composition A4, and we can continue doing this if we choose to until we get nearly pure A in the vapor, and we'll then get a liquid of nearly pure B. So as we move the vapor phase to the right, the liquid phase is going to move to the left, right? As we enrich the vapor in A, we're going to remove the A from the liquid phase, which means the liquid is getting enriched in our less volatile component B. So we're moving the liquid phase to the left, we're moving the vapor phase to the right. Alright, so the efficiency of a fractionating column is given by a number of theoretical plates. This is the number of vaporization and condensation steps that are required in order to achieve a condensate of a given composition from a given distillate. So if we go back here, we've gone two steps. So in this case, to achieve the separation that we show over here, the column has to correspond to 3 theoretical plates, right? We've got one vaporization occurring here, then we condense that vapor, and we vaporize again in a different place maybe, and then we condense that vapor and vaporize a third time. So to move from this point to that point, or then the subsequent liquid, which would be a point down here, to move from this composition to that composition requires 3 theoretical plates. If we want to achieve the separation that we show over here, now the column has to correspond to 5 theoretical plates, so we have to go from here to do a similar sort of composition. Note that now these lines are closer together than they were on the last slide. Right? So the farther apart these lines get, the farther we can move over with each step. So the closer the lines get together, the more steps we have to take in order to get the same increase in our composition. So here we have 1, 2, 3, 4, 5 theoretical plates to move from this point to that point in composition. Alright, so our temperature composition diagram that we've used above, those are for ideal solutions, but many of our important solutions are non-ideal, so we're going to look at those, and we'll call these azeotropes. So if our AB interactions are stronger than our AA and BB interactions are, then this means that the vapor pressure of the mixture is lower than it would otherwise be, because the those AB interactions are pulling together stronger than the molecules are held together stronger than they would be as pure A or pure B, and this means that the vapor pressure is going to be lower. It's going to be harder to separate those molecules, and this means that there's a maximum in our temperature composition diagram, as we see over here. Right, so we have this maximum point here. Right, so the excess Gibbs energy, GE, is negative, which means mixing is more favorable than it was for an ideal mixture, for an ideal solution. So this may be something like nitric acid and water. So if we mix nitric acid and water, we get energy out. And so we may have a case where it looks something like this. On the other hand, if the AB interactions are weaker than the AA and BB interactions are, and this means that the vapor pressure of the mixture is going to be elevated, because now it's easier to separate the A and B molecules from each other than the A molecules from themselves and the B molecules from themselves in the pure A and B. And this means that there's a minimum in our temperature composition diagram that we see something like this. And in this case, the excess Gibbs energy, GE, is negative, so mixing is more favorable than the ideal. And so this is something like ethanol and water. All right, so let's consider a liquid of composition A on the right side of the maximum. Right? So we're over here somewhere. So we're going to look at this spot A. So when we heat up our liquid, and we raise the temperature, we're not changing the mole fraction at all, so we're just moving up this dotted line, this vertical dotted line. And at some point then, we get to the boiling point at A2. Well, the vapor phase has a composition A2 prime, and it's more enriched in our in A, our more volatile component here. And then as the vapor is condensed elsewhere, and then the remaining liquid, right, the remaining liquid will have moved to the left. If we've enriched the vapor in A and then removed that A, we've preferentially enriched the liquid in B. We've removed some of the A, and that means that now we move to the left, and then we have to go to a slightly higher temperature in order to boil that liquid, and we get a vapor at A3 prime, let's say. Then we can remove that vapor and condense it elsewhere maybe, and then we take our subsequent liquid. Well, again, we've moved to the left, so now we're maybe at composition A4, heat it up again, boil it, and now we have vapor with a composition A4 prime. And in this way, the composition of our liquid is increasing in B as A is being removed with our vapor phase. And this means that we're moving closer and closer to this point where our red and blue curves are intersecting. But once our liquid gets to that point, this point here, at this mole fraction B, right, composition B, mole fraction of A at this value B, whatever it happens to be, this is at the maximum temperature, then that means that the vapor phase, the red curve, and the blue curve are the same place. This means that our vapor has exactly the same composition as the liquid, and that means that when we vaporize it, the composition is exactly the same, so we're not enriching the vapor in our mole volatile component because the composition is exactly the same as in liquid. And this means that our mixture has formed what we call an azeotrope. This is for the Greek word for boiling without changing. And so we have an azeotrope. So now let's look at a system with a minimum in our temperature composition diagram. This is also azeotropic, but this is azeotropic in a different way. So again, we have a minimum. So we still have the red and blue curves meet here at point B, but note that now it's the minimum as opposed to the maximum as it was before. So if we start with a mixture of composition A1, so again we're starting over here, and we heat it up, so we move up to the boiling point at A2. The liquid boils, that means the vapor has a composition of A2 prime. Note that now the vapor is less, is not enriched in A, it's been enriched in B. It has less A in it, so we move to the left. And now if we condense that vapor, and we're discarding the liquid now, the liquid phase would have moved to the right and thus up on the this blue curve. So if we condense this vapor back to a liquid, well then it'll be back at point A3. Note that that's the same composition as we have here at A2 prime. Well, that will then boil to give us a vapor at A3 prime. That then condenses to give us a liquid at A4, and we continue doing this over and over and over again until eventually we get to a mole fraction of B. But in this case, we have a mole fraction of the vapor, not the liquid, at our azeotropic composition, right? So in this case, we've had to take our vapor, condense it, and then boil it again, and take the vapor of that, distillation, and we're throwing away or removing the liquid phase. Before, we were throwing away the vapor phase, condensing it elsewhere. But in this case, now, so with a minimum, we are moving our mole fraction of the vapor towards that minimum point, that minimum composition. Whereas with the maximum, we were moving the composition of the liquid towards our maximum point. Okay, so we can't use distillation to obtain a vapor beyond composition B. So if we want to go past this point, if we want to go to the left of that, we can't use distillation to do it, because once we've reached B, when we evaporate our liquid to get a vapor, we have exactly the same composition. So you can continue doing this process over and over and over again, and you will never move past point B. Note that you also won't move past point B from the left side. If you're over here, and if you condense a vapor back to a liquid and then boil that, and then condense back to a liquid and boil that and condense back to a liquid and so on, you move to composition B. So from either direction, the composition of the vapor is trending towards B. Note that on with the last kind, with the maximum point here, from either direction, you are trending towards a composition of the liquid at composition B, right, with that maximum point. All right, so if we look at something like ethanol and water, is a famous example of this. So ethanol and water, that mixture boils at 78.1 degrees when the mixture is 4% water and 96% ethanol by mass. And this means that with distillation, if you have a 4% water, 96% ethanol mix, when you vaporize that liquid, the vapor has exactly the same composition. So you can't use distillation to get pure ethanol. It can get pretty darn close. You're getting 95, 96% ethanol out of it, but you can't get purer ethanol than that. So this is why when somebody goes to purchase alcohol, you can't get alcohol that is higher than 96% by distillation. Now, chemists can do this with other means. We can put in, say, a dehydrating agent that will remove the water from the ethanol. But in general, it's not worth it. It's too costly to do that. So for human consumption of alcohol, we leave it at 96%, and most of the time it's way less than that because it tastes really bad. So know that the normal boiling point of water is 100 degrees C, and the normal boiling point of ethanol is 78.37 degrees C, but the boiling point of our mixture here for 4% water and 6% ethanol, that's a lower boiling point than even the ethanol was. Right? So our mixture is boiling at a lower temperature than either the water or the ethanol were by themselves. Right? So this point B is a lower boiling point than either the pure ethanol or pure water. Right. So now let's talk about immiscible liquids. So in order for this discussion, we're going to assume that the mixture is being stirred or agitated in some way, because otherwise the top layer is going to occlude the bottom layer and prevent the bottom layer from vaporizing. Right? So we're assuming that we're stirring it up, or it's being agitated in some way. So we have a case that looks something like this, where we have some darker areas and some lighter areas. We have two different phases, and they both exist at the surface here. So at equilibrium, there's a tiny amount of A dissolved in B, if it's immiscible, and there's a tiny amount of B dissolved in A. And this means that the total vapor pressure is close to the vapor pressure of pure A and pure B added together, because we know that the vapor pressure of A will be the mole fraction of A in the phase that it's in the liquid. Well, if it's mostly A and just a tiny amount of B dissolved, well, then the mole fraction of A is really close to 1, which means that the vapor pressure of A is really close to the vapor pressure of pure A. And likewise for B. So if the total vapor pressure is raised to atmospheric pressure, this means that boiling occurs and our dissolved substances are purged from the solutions. But boiling agitates the mixture, and this means that each component is still saturated in the other one. So as the bubbles are coming out and the solution is being boiled, it's also being mixed, and that means that as we vaporize A from the solvent B, well, more A is being introduced, and so they both stay saturated in the other one, which is going to be key in a minute. So note that the boiling point for the immiscible mixture is lower than that for the pure liquids separated. Right? So the boiling point for this mixture is going to be less than the boiling point for this case if we have, say a test tube and we divide it down the center and we put pure A on the left and pure B on the right. The boiling point here is going to be different than the boiling point over here. So the pure liquids, pure A, will boil when its vapor pressure equals the atmospheric pressure, not when the sum of the two equals the atmospheric pressure. Right? So A will boil when A's vapor pressure reaches the atmospheric pressure, and B will boil when B's vapor pressure reaches the atmospheric pressure. But our mixture will have a total vapor pressure of the vapor pressure of A plus the vapor pressure of B. It's that total that needs to reach the vapor pressure, that needs to reach atmospheric pressure in the mixture case, which will mean that it will boil at a significantly lower temperature than either one by themselves. And so this effect is used in steam distillation, which allows us to have some heat-sensitive, water-insoluble organic compounds to be distilled at much lower temperatures than their normal boiling points. And so note here that the vapor composition is proportional to the relative vapor pressures of the components. So this means that a low vapor pressure organic would be at a low concentration in our resulting vapor or condensate. So if we were doing this with steam, we're going to have mostly water, a little bit of our organic. Now, if we condense that and they'll form two separate phases, well, we'll mostly get we'll be able to separate the water from the organic anyways, and so it doesn't matter that much. But this is a big problem if our vapor pressure of our organic is really, really low. Like that's then a problem. So that was temperature composition diagrams.